wanted to start just by giving you an overview of the areas that I do research in. So I do very interdisciplinary research, and it really covers 3 areas in particular. So ubiquitous computing, human-computer interaction, or HCI, and then education and educational technologies. So what I do is I basically design and engineer new ubiquitous computing technology with a particular emphasis on technology that empowers other people to design and build their own ubiquitous computing systems. And then the other half of the research that I do is kind of test those systems that I've developed in real-world settings. So give those systems to users and see, can people actually use them? What sort of educational potential do those systems have? How do people use the systems that I've developed? So this work has really been motivated by a desire to communicate what I see as the tremendous creative, intellectual, and practical power of computing and electronics to as many people as I can. So let me just give you a quick example of kind of work in these areas. So as Gaetano mentioned, I'm kind of wearing your light wall, so I'll go ahead and turn it on, and we'll do a little bit.
More interesting than ours.
Yeah, you can reprogram it, you can do all sorts of things. So yeah. So this is actually a little cellular automaton program. I was a physics undergrad, so this is an ideal gas simulation. So this is an ideal gas cellular automaton program. So you can actually do kind of computationally interesting things on substrates like this. So this is an example of kind of an interesting ubiquitous technology. So some work went into figuring out how to engineer this device, particularly working with off-the-shelf electronic components. It's actually been quite robust and wearable, so I wear this quite a lot. It's about 2 years old now. I've washed it about 10 times. I do hand wash this guy. I've been a little afraid to throw it in the washer and dryer, but it's been pretty sturdy and has held up pretty well. Not entirely without a few repairs, but pretty well. But perhaps the more interesting aspect of this project is that when I built this display, I went through a detailed documentation project as I built it, and I posted on my website kind of do-it-yourself instructions that explained how someone could build their own one of these devices. Those instructions eventually turned into an article that I wrote for Craft magazine, kind of the sister publication to Make magazine, which probably at least some of you are very aware of. And it seemed to strike a nerve in kind of hobbyist communities around the world, and it got a lot of interesting feedback, so that was a really exciting experience for me. So this is just one simple example of kind of the style of work that I do. So again, kind of developing new technologies and then trying to find ways to democratize that new technology. So make that technology accessible to people out there in the real world and see what they do with it. Turn this guy off for now. So I am not the only person doing research in this space. I think I'm part of a growing and really exciting movement, I think, in ubiquitous computing that's exploring this democratization of ubiquitous computing. So I'm just going to point out a few other kind of interesting spots in that space. So in a large sense, I kind of think of the founder of this field as Mitch Resnick and the work that he's done for a long time at the MIT Media Lab. So he and his groups developed a series of microcontroller platforms that allow kids to work with robotics, so that allow kids to build their own robots. So these were called the Crickets. And they eventually developed into the Lego Mindstorms robotics kits that are now incredibly popular and have had a really wonderful and fantastic impact on engineering education, I think. This is a photo of the most recent version of the Cricut. This is called the Pico Cricut. And then it's actually trying to kind of extend this universe kind of beyond just working with robotics and get kids engaged in other sort of what I'll call ubiquitous computing applications. So that's one interesting kind of spot in this space. Here's another one. So this is an image of the Arduino 10.000 microcontroller. Of course, there are a lot of microcontroller platforms out there, but the Arduino is unique for a number of reasons. So it's an incredibly cheap device. It's also an entirely open source project. So all the software and all the hardware is entirely open source. But perhaps most importantly, there has been a tremendous community growth around this microcontroller. So it's being widely adopted by all sorts of different communities, from artists to engineers, and is really becoming kind of a standard platform for doing kind of all sorts of diverse electronics projects. So here is another interesting participant in this space. I'm not going to linger on that one, but. So there is also, so this is another academic and really powerful academic contribution. This is work that's being done at the Stanford HCI lab, so by Scott Clemmer and his students. This is a screenshot of one of their software applications. So this software is called D-Tools, and it basically, the idea is it lets designers and other people who are not necessarily hardware experts think about hardware in ubiquitous computing prototypes. So they can design and kind of lay out the behavior of the device using this software application. And then there's a companion kind of microcontroller platform that allows them to then prototype the hardware. They've also done a wonderful job of plugging into existing kind of user communities and hobbyist communities. So a lot of their software applications are now compatible with the Arduino board, and they're involved in that community in really interesting ways. And then finally, this is an interesting contribution from the commercial sector. So SparkFun Electronics is just an online electronics company. But what they've done that has really added to this space is they kind of seem to dedicate themselves to searching for exotic hardware devices and then finding a way to get those devices to the people in ways that hobbyists and researchers can use them easily. So they're, again, making another just really powerful and unique contribution. Okay, so computational textiles. So what is this domain exactly? So computational textile researchers strive to integrate electronics and fabric as seamlessly as possible. So these devices should contain computational functionality while having all the natural qualities of cloth. So they should be soft and stretchy and flexible and washable. So here are some examples of computational textile devices. So on the left is a dress that was designed and built by Maggie Orth, one of the pioneers in this area. And this is a really simple and playful device. So this is a dress with lots of LEDs that are embedded in the skirt. And as the wearer walks along, the LEDs kind of twinkle on and off. So there are simple motion sensors in the skirt that make that happen. Shown in the middle is a device that you can actually buy now. This is a popular commercial product. In fact, I have one version here that I did not build. Parts of it I did not build. But this is a jacket that has iPod controls mounted on the wrist of the jacket. So the idea is that you can wear this when you're skiing or snowboarding, and you can, control your iPod as you go around the mountain without having to, say, take off your gloves or do other stuff like that. So this jacket here has a similar kind of embedded soft keypad that lets you do that. Shown here is a more serious application of this technology. So this is the Life Shirt. It's a device that was developed by a company called Vivometrics. And this is a wearable medical monitoring device. So it has all sorts of embedded sensors that take continuous measurements of the wearer's vital signs. So it measures blood pressure, heart rate, breath rate, has some measurement of how the person's activity level, and then it stores that data, and that data is available later on for a doctor or medical researcher to download. Presumably also the user could look at that data and get a sense of his or her own health. So this gives you a sense of the tremendous possibilities for research in this area in the medical arena. So one of my first projects is what I call the electronic sewing kit. So I developed this really simple kit of soft electronics, and then did a bunch of kind of user studies with all sorts of people where kind of introduced them to these materials and had them play with just soft electronics. So this is a picture from one of our early user studies. Now, of course, this is not a very rich domain, right? So we were just playing with LEDs and simple series and parallel circuits, not a whole lot you can do. So clearly the next step was finding a graceful way to integrate computation into these types of activities. So a next step along that path was this project that I call Quilt Snaps. So this really took off where this sewing circuits project left off. So in a similar way, people would receive, participating in a Quilt Snaps activity, they would receive kind of a blank quilt square. But in addition, and they would also receive electronics that they could sew into that quilt square to make a simple circuit with. They would also receive crafting materials so they could decorate the square however they wanted. But then once that decoration process had happened, the quilt squares can be snapped together to create these simple directed graphs that animate kind of flows of information through the quilt. So kind of here's what this guy looks like now. The flows of information are indicated by the arrows on the patches. You just get simple kind of flows of information through them. Different sensor strips snap onto the patches, and you can do things with light sensors and motion sensors and so on. And this is a blank square, so it gives you a sense of what it looked like before people decorated them. So this was all fairly simple and preliminary work that I did, but I think there are a couple of things here that are noteworthy and interesting to just stop and think about. Most important is just the integration of electronics and computation with arts and crafts materials. So I think thinking about electronics and computation as just another material for arts and crafts is kind of a strange, but also kind of a powerful way to think about things. So it's a very different context and one that we're not used to thinking in, but it leads you in interesting directions. So we'll kind of keep that on the stack for later. Okay, so now I'm going to step back a bit from specific projects and just talk about techniques that I've developed for engineering electronic or computational textiles. So I've developed several ways to integrate cloth and off-the-shelf electronic components as part of my research. So some of them are electronic sequins, socket buttons, which is what you see a picture of here on the right, and fabric printed circuit boards. So I'm going to spend just a little bit of time talking about fabric printed circuit boards and how they're made. So basically, I start with a piece of conductive fabric that is commercially available from several retailers. I then attach an adhesive to the conductive fabric. And so we have a layer of conductive fabric, a layer of adhesive, and then a layer of paper backing. That substrate then goes into our laser cutter, which is what you see a picture of here. So the laser cutter is really fantastic and powerful tool. But the laser cutter then etches a circuit pattern out on that conductive fabric. And so what comes out of the laser cutter looks something like this. So what you're seeing is the conductive fabric is on the other side. You're seeing the kind of adhesive side with the paper backing. I then peel off the paper backing just in the areas where I want the circuit to adhere to its fabric backing cloth, and then iron those two together. And then you get something that looks like this, where I can peel away the parts of the circuit that didn't adhere, and we're left just with kind of the PCB that we wanted originally. So it looks something like that when it's finished. And once you have it, this PCB really functions just the way a traditional PCB would. So you can solder electronic components to it, like this, for example. So that is a 32-pin microcontroller in the TQFP package. So that gives you a sense of the scale of these devices. That, I think, is about as small as I can get with this stuff, but it's pretty small and interesting that you can get that tiny. I'll also mention that very naturally these circuits can be multi-layered. So we can put a layer of conductive fabric, a layer of non-conductive fabric, and then a layer of conductive fabric. So this, it turned out, was a really powerful way to quickly prototype multi-layered circuits. So that was kind of an interesting byproduct that I didn't expect initially from this process. So this is one example of a technique that I developed for working in this area.
How do you do connections between levels?
Yeah, so you can solder things. You can also, the adhesive that I use is this heat-activated adhesive. And actually, when you iron a piece of conductive fabric, one piece onto another, you can get conductivity through the adhesive so that you can glue them together, and then they're then conducting between layers. So, and then you can also just kind of, that's big. Any other questions about this, or? But so this is one example of a technique for working in this area. But I think this is just an example of work kind of in a larger space that I'm really interested in, which is the intersection of computation on the one hand with new output devices and new materials on the other. So I especially think this is a really important direction for ubiquitous computing research to go in. So let me just give you a couple of other examples. So with new output devices, so this was an example of the use of the laser cutter, but there are also 3D printers. There are computer-controlled embroidery machines, computer-controlled milling machines. I think so an exciting way to think about computation is to think about these devices as the output of your programs, and kind of what implications does that have for the types of things you can build. So thinking about things that you can programmatically build but out in the physical world. So I think that's a really interesting avenue of research. And then new materials, another really exciting area. So this was an example of working with conductive fabric. Of course, there are also conductive threads. There are all sorts of cool flexible electronics that I can play with, so flexible solar panels, flexible batteries, all sorts of thin film technologies available. I just read an article in Nature. A researcher at Georgia Tech has developed kind of a fabric that generates electrical power as it kind of, the fibers rub against themselves. So these are all really exciting things that I think we as UbiComp researchers should just be grabbing these developments and seeing what we can do with them. So I think that's going to be a really fascinating research area. Okay, so to return to the meat of my talk here, back to projects that I've worked on. So another thing that I did kind of early on in my research, again, experimenting still with materials and techniques, was to design and build several wearable displays. So this was, again, trying to see what I could do with these materials and what sort of things that you could build that were interesting in this kind of wearable and soft design space. So you saw an example of this guy, which I'll turn around. I also built what I think is a more interesting wearable display, which is this beaded bracelet that I'm wearing. So this also has a embedded accelerometer, so we can do some things there. So I can shake it and add more particles to that ideal gas simulation. I can also kind of switch the mode on this guy. And just if I can press down the switch there. And we can do other things. So that's a pattern that's probably familiar to at least some of you. That's that game of Life Glider. So that's kind of fun. And this is also Bluetooth enabled and makes use of more interesting kind of materials. So there's a super thin, flexible lithium-ion battery that's powering it. And again, makes use of conductive threads and conductive fabric to make it really thin and super flexible and stuff. But again, what ended up being perhaps most interesting about that project was the do-it-yourself instructions that I published. So as I mentioned earlier, I got some really positive response from that. So it seemed like it really tapped into a nerve in a community, and I got all sorts of emails from people around the world who read the instructions and were excited about them. So I got emails from people as diverse as a grandmother who said that she was going to use the instructions to embellish some Teletubby bags that she was knitting for her granddaughters, to like double E guys who were, telling me why like I should rewrite my C code for the like cellular automaton stuff. So that was a really fascinating experience. So this, I did also get pictures and videos from a few people who were excited about what they built and wanted to show me. So I just wanted to stop and show you one of those. So this is, I wanted to start by showing you the email. This is the first email that this woman sent me. So she says, "Thanks for publishing your how-to for the wearable LED display. I'm learning all about electronics a little late. I'm 26. In order to make your LED display, I have sort of taught myself starting with a kid's LED kit." So that gives you a sense of where she started. Let me show you what she built. Unfortunately, you're not getting the sound, which is kind of the coolest part of this stuff, but you can imagine this really heavy-duty punk music soundtrack here. So each skirt has an array of 4 by 20 LEDs, and they work. So let me tell you a little bit more about the instructions that I wrote and why this is such an impressive accomplishment for this woman. So the instructions that I wrote, to build that project, you need to do things like install the AVR GCC compiler on your machine. And that requires all sorts of command line configurations and worrying about stuff like your path variable. On the hardware side, it's kind of equally ugly. So you have to buy a really ugly hardware programmer, interface with that. To load the code onto your chip, you also requires kind of this command line interface stuff. You probably have to edit your make file to get it to talk to the programmer in the right way. So needless to say, it's kind of a really grungy, hackerly set of instructions. So I was so excited and happy that this woman went through the process and actually completed a successful project. But this was actually a more common response to my posting. So I have some trouble following your steps. I hope you give me some quick advice. In your step number 4, I can configure but not install GCC on my Mac running 10.3.9 during make. Get that crash. I have no idea what this guy's problem is. I really don't want to spend my time trying to figure out what his problem is, but at the same time, I feel terrible that I kind of promised people this exciting and new and interesting experience, told them that there was this thing that they could do that was really cool and new, and then I led them to this miserable and unhappy failure. This really led to me thinking about building usable and truly usable tools that would allow other people to work in this domain. So that led to my development of what initially I called the E-textile construction kit. And so what this is a set of hardware and software tools that allow novices to fairly easily build their own computational textiles. So at the heart of the hardware for the kit, which is of course a little bit of a misnomer since everything's kind of fabric-based, but at the heart of that is the microcontroller component. So that was the initial microcontroller component. And then it was accompanied by a set of sensor and actuator modules. So these are all based on the fabric PCB technique. So all the circuit boards for them were made out of conductive fabric and traditional fabric. What you have here in this particular set is a temperature sensor, a light sensor, a little switch, fabric-based switch. This is an infrared transceiver. That's a on-off switch made out of conductive Velcro, another cool material. And then finally some assortment of output devices. So there's a vibrator motor, some LEDs, and a little speaker up there. So just some more specifics about what this kit looked like and what it's made out of. So the microcontroller that I've ultimately ended up using is the Atmega 168V. This is it in its DIP package. Ultimately, the hardware for the microcontroller also contained a reset switch, a decoupling capacitor, a status LED. In this particular version, so remember the solder joints on the fabric circuits need to be protected in a hard coating so that they won't break with the bending of the cloth. And so on the back, where all those electronics are soldered, there's kind of a coating of a hard plastic resin to keep the electronics protected. And that hard footprint for this guy is about 46 by 21 millimeters. So that's about roughly 1 inch by 2 inches, so it's not so great. Actually had a vertical height, so including that hard plastic bottom, and then the DIP package extending had a vertical height of about 12 millimeters. And then it had 15 stitchable I/O pins. So each one of those is made out of conductive fabric and can be sewn to cloth. And the way that you make connections with this kit is to sew components together with conductive thread. So to attach, for example, this light sensor, I would attach the sensor tab there with stitching in conductive thread to say tab A0, and then the plus and minus tabs, I would sew through those with conductive thread and attach them to plus and minus on the microcontroller. So this is what the original version looked like. But I've recently, just in the past year, kind of extended that quite a bit and made a much nicer package for this stuff. So this is the current incarnation of the LilyPad Arduino. So this is the microcontroller piece. And as you can see, it's kind of it's very different. It's a big kind of step up from the previous one. So it's a lot prettier, for one, which I think is very important, but also technically just better in all sorts of ways. So it's the same electronics in there, so, but it's using the surface mount version of that microcontroller, so things are really tiny. So the hard footprint there is 20 by 20 millimeters. And the vertical height is where you really win, so that's just a few millimeters thick there, so it's you know, really approaching something that's very reasonably wearable, as the old one was pretty clunky. And the size has really shrunk, and then you've also gained in kind of computational power, so we have actually a lot more I/O because they're laid out in a much more kind of elegant and natural configuration. So we've got 23 in this version as opposed to 15 in the previous one. And then finally, we have some nice laser etched labeling of all the I/O pins. So the labeling on the previous version was all done by hand, and it was pretty kind of awkward and kludgy, and this allows me to automate that process, and it also really adds to the aesthetics, I think. So here's what the software side of the kit looks like. So for software, I developed the firmware on the microcontroller to be able to talk to the Arduino programming environment. I also did some tweaks to the Arduino programming environment and wrote some custom libraries for it. So I did not write this programming environment. This is the language and IDE that's used by the popular Arduino microcontroller platform. This was a conscious choice. I felt that I could really leverage the fantastic communities that had developed around the Arduino, and also make use of this fantastic and kind of robust tool that already existed. It has fabulous documentation, fabulous tutorials and stuff online. Although there are some limitations here, and I'll get back to them in a second. But for now, this is what it looks like. So you write programs in C. You have basically this is the form of a program. You have a setup section and then a loop section, which is the main execution section. All the compilation and the uploading takes place through this kind of single integrated programming interface. Okay, so this is the kit that we developed. Now what can you build with it? So I'll show you a couple of demos of sample projects. Here you can see how the LilyPad gets sewn into things to be connected with other things. This was one sample project. That's a hat with a pom-pom and that has an embedded RGB LED and temperature sensor. So the pom-pom is continually giving you a reflection of the ambient temperature. So that was just kind of fun. Here's another one that I just kind of built. This one is actually quite useful. So this is my biking jacket now. And we have, and when it's dark out, I can put it on flash mode. So the idea with these two examples is to provide examples of devices that kids and other people who are really new to programming and electronics would be able to build in the course of a week-long workshop, or a workshop that might take place all day over a few days. So just to give you that context for these types of examples. Okay, so I built this kit. Now, what sort of stuff did I do with it? So the next step was that we held several user studies based around the kit. So I held 2 high school electronic fashion classes. So each of the workshops that I taught, I billed as learn to make your own electronic fashion. And in those 2 high school classes, I had a total of 21 participants. I should mention that in each class, I capped enrollment at a certain number. So we had full enrollment in each instance of the class, so that was fun. But Anyway, so those were the numbers. We had a total of 21 participants. Out of those 21 participants, 16 were girls and 5 were boys. I taught 2 day-long workshops with adults. In this case, where I haven't noted the gender, that means the participants were kind of by invitation, so I feel there's nothing you can read from gender information there. But in those 2 workshops, we had 9 participants. 1 week-long workshop with teens and adults with 7 participants, and then finally 1 week-long workshop with a group of teens. We had 10 participants, 9 of them were girls, and 1 of them was a boy. So in terms of evaluation, this ended up serving as really an iterative development process. So where I tested out kind of the usability of the tools that I had developed, and from the user experience kind of went back and built a newer and kind of better version of the kit. This also served as a platform for me to develop a curriculum for a computational textiles course. And then kind of beyond this kind of usability and kind of figuring out what this domain in the educational realm would look like, we did begin to assess educational potential. So can you teach basic electronics and programming concepts through this medium? I think clearly yes, but probably is something that we should look at in more detail. So looking at gender issues. So you can see from these numbers, so in all the cases where participants were self-selected, we had pretty noteworthy stats there. So, and then finally looking at student motivation. So that's just a topic I'm really interested in thinking about and looking at more in the future. Okay, so here was the structure. This was the basic structure of the class. So the courses start out with kind of a very whirlwind introduction to electronics and programming via the LilyPad kit. So this shows you how the LilyPad module is hooked up to a computer for programming. And this shows how we kind of would attach other electronics components during kind of this prototyping learning phase. And this is a sample program that gives you a sense of how people would do things like control RGB LEDs. So after that whirlwind introduction, the students would go through a fairly rigorous design and prototyping phase. So I initially started working from a Lego robotics course as kind of a template for the courses that I would teach. But the crucial difference between this medium and that of building a Lego robot is that when you're working with Legos, you can take stuff apart really easily and rebuild and iteratively work on your designs. Here, for better or for worse, once you start sewing something, you've really invested a lot of labor into that thing. So you're really committed. So because of that, this activity really takes on the feel of a much more traditional engineering activity, and it's important to invest in some thoughtful design kind of early on in the process so that you don't ultimately end up with a failed project. So once that is done, the students work on constructing their project. And again, I found that especially in the early phases, it's best if that's fairly guided. So I force them to kind of attach components one at a time and make sure they leave time for stuff like debugging, which of course they would never do unless you made them do it. So they never expect that anything's going to go wrong.
Why not a simulator?
So that is definitely, something I've thought about, and I think that might be something that I could do an interesting project to take on in the future. Definitely an interesting possibility, and possibly that coupled or tied tightly to a programming interface would be particularly interesting. That being said, there are problems here that maybe especially that upper left-hand image hints at that a simulator does not capture. So you can see how likely is it that this microcontroller is going to fry there if I don't have her trim some threads, and having just all sorts of real-world engineering problems like shorts and just all sorts of issues there that you really need to be working with the tangible physical stuff to work out. So this kind of shows how you can prototype and build at the same time in a certain sense. So you can use alligator clips to do that. And then this is a kind of a close-up picture of a finished design that was really beautifully thought out and really beautifully done. So this is a 13-year-old girl built this. And then finally, each class culminated in a fashion show or an exhibition where people got to show off what they had built. So here's some photos from there. So these guys were really cute. They were such like tough, bad guys, but they had a lot of fun, so that was neat. The girl showing off her circuit and explaining how it works. This was a very interesting image for me. So this shows people actually using the wearable device that they had built in an interesting kind of social interaction. So the girl in the picture built the wearable device that she's wearing, and it's this touch-sensitive shirt that when someone squeezes her waist, it makes funny sounds. And these teenagers in this workshop were very happy to have that excuse to kind of feel each other up around these wearables. So I think this is an interesting pointer for future research. So the social role, but seriously, yeah, the social role that these things can have in our lives, and that there's interesting stuff to look into in that space. So this is a video just showing some of the different things that people built. You lose some context here without the sound, but I can try to explain in places where it's not clear. So here it's an RGB LED whose color changes in response to the light sensor data. And then on the inside of a bag is this light that comes on when you open your bag. A light comes on to illuminate what's inside of it so you can see. And then when you close it, the light goes off, so you're not wasting power. See the circuit. And this was a really lovely project. So I don't know if you can quite see there, but each LED is matched to kind of a magic 8-ball, like saying like most definitely, answer uncertain, ask again. So you would ask this shirt a question and then press a button and it would randomly spit back an answer to you. So it's very voodoo-ish, Ouija board. So we had this was a fun thing to play with. Oh, and here you lose the sound, so what these are doing is kind of emitting different sounds depending on kind of where you touch them, and you can see some with the lights there, but you're not getting the musical effect. It's really video game-like beeps. It's not terribly impressive, but it's kind of parasitic, power harvesting wearable. Yeah, so those are some examples of the stuff that people have built. And here's some student feedback. This is all collected from the most recent workshop that I did that ended during the summer of 2007. So I just want to stop and touch on some of these feedback points which I think point towards interesting future research areas. So was there anything in the class you found particularly hard to do? So these two things came up over and over again. So sewing was hard for some people always. And then kind of more tellingly, I thought this was a strong, kind of poignant quote. So I had a ton of trouble programming. It was very confusing to me. So I think that, while the Arduino programming interface has many benefits, I don't think it's the best way to introduce kids to programming. And I think a lot of work really interesting work could be done in thinking about programming interfaces for these materials and devices, trying to make that experience more friendly. Do you think you might take future classes in electronics or computer science because of your experience in this class? We had very positive response from that question I'll mention, so that was interesting. But I want to stop and look at this middle quote. So yes, because I intend to be an astrophysicist or a mathematician. Also, I'm interested in fashion design and modeling. So I think that quote captures some quintessential essence of American girlhood. There's something, yeah, that, and that we are able to tap into that, and I think that's powerful. So not everyone was infatuated with the class, so we did get, some, no, I'm not interested in this stuff. I just tried it out, and it's not really interesting. So here's another interesting one. So are you interested in building electronic fashion at home on your own time? This girl says, yes, I think electronic fashions would be cool presents. So I think that there's something deep and interesting hidden there in that quote as well. So what does it mean when you give a computational device away as a present? That's a really different way of thinking about a program or an electronics project, thinking of it as something that you give away as a gift. So I think that thinking about computation and electronics in these contexts can have all sorts of interesting social implications. And that, that's a pointer to one of them, but I think there are lots of other interesting ones. Another one here at the bottom, actually. So this was an email that this boy sent me after the end of the class, so it kind of warmed my heart, but there's an interesting kernel in here. So I just wanted to tell you that my friends thought my hat was so cool. I'm just sending an email to say I loved your camp so much, yay. But I think this is telling. So my friends thought my hat was so cool. So this guy built this computational electronics thing, then went and showed it off to his friends, and they thought it was cool. It seems like there's something we can take advantage of there, yeah? Like something, we should be able to exploit that. Okay, so I've been really excited to teach these workshops and have these experiences with people. But unfortunately, all of the kit components for these workshops were hand built by me. So hand cut on the laser cutter. I mean, not hand cut, but cut on the laser cutter by me. The electronics hand soldered onto the boards. So needless to say, this was a very labor-intensive, time-consuming process. So I felt that the types of results that we were getting from these workshops had really interesting implications, and I really wanted to be able to do large-scale studies, longer-term studies. I really wanted to empower people to take this on as a hobby, so I really wanted there to be a way for them to take these materials home and work on them at home, but I couldn't do any of those things because of this accessibility problem. So in a first solution to this problem, I've recently partnered with SparkFun Electronics in Boulder to release a commercial version of the E-textile kit, the LilyPad Arduino. So here's what it looks like right now. So unfortunately, what we've lost is that the kit is no longer fabric-based, so it is traditional hard circuit boards that it's based on, but it is still sewable and at least looks kind of different from your traditional electronics, so that's kind of fun. But what it consists of right now is the microcontroller module, so that's what you see in the center. There's a power supply module that takes a single AAA battery. There's an accelerometer, a little speaker, an RGB LED, a vibrator motor, and a little light sensor. So I just want to mention that my work so far has really been focused on kids and kind of what they can do with a kit like this. But I think the audience and the potential of it definitely extends beyond there. And there are all sorts of interesting, more sophisticated applications that one could use the kit for. So I'm just going to pop up a couple of examples of what I like to call LilyPad backpacks or something. So this is a Bluetooth module. So if you notice on the LilyPad microcontroller board, there are 4 pins that come out, so a male header there with 4 pins. That's bringing out the USART on the microcontroller, so it allows the microcontroller to communicate, basically function like communicate serial data to all sorts of things. So I can just, using jumper wires or whatever, I can attach that Bluetooth module to the LilyPad and all of a sudden have a Bluetooth-enabled wearable. Do all sorts of things there. And if you guys are interested later, actually, I have some Bluetooth-enabled stuff here. I can give a demo of that if you're interested. So, and here's a really another really interesting point in this space, I think. So this is a data logging module. So this circuit accepts serial data and then writes it to an SD memory card. So I can fit a really tiny 1 gigabyte memory card in there. And again, just plug that right into the link on the LilyPad. So imagine, I could sew out all sorts of accelerometers attached to that LilyPad and then walk around all day logging that data to that memory module. So completely doable right now. Okay, so that gives you some sense of the LilyPad and its capabilities. Now let me just step back and kind of return to this issue of democratization. So I'm going to be kind of mean. So what's wrong with computer science? And don't you double E people think that you're getting away easy, because we could just cross out computer science and put electrical engineering there too, I think. So let's look at some traditional CSEE things here. So yeah, here's slash dot. Here's some traditional electronics hardware. Here's some really cute boys kind of working on Lego robotics projects. I just realized I left out a picture, which was a screenshot of my command line compiler garbage, like spit back at me from like GCC. But anyway, imagine that as another point in this space. So when I look at these pictures, some themes emerge. So number one, none of these things are particularly beautiful. So there's a certain, even the color palette here. So it's not so aesthetically interesting. And aesthetics are something that are really important to me as a person. I think they're important to a lot of people, but they're nowhere to be found here. So that is kind of problematic, I think. Also,
you're the same color as that circuit board.
Yes, you're true. Where's my pink jacket? See, I don't even know. It's seeping into me. I do have a red coat. Yeah. But so another thing here, and imagine that command line interface in your head, is how inaccessible some of this stuff is. So yeah, command line interfaces not so accessible or user approachable or user friendly. But more important than this domain being practically accessible, I think it is culturally not so accessible. So Yeah, sometimes I read Slashdot, and then sometimes I can't stand to read it because I just feel it can be awful. So it can be misogynist, and it can be all sorts of terrible things. It's just not terribly culturally friendly or culturally diverse. And these guys, so I don't want to pick on these guys. They're great. They're fantastic. Probably a lot of us were a lot like these guys when we were kids. But I think that that's a picture, too, of cultural inaccessibility. So not everybody wants to do what those guys are doing. And I think what we can't do is limit and define computer science as just what those boys need and want to do. To soften what I said earlier, I don't necessarily think there's anything wrong with these cultures. Each of these things is wonderful in a lot of ways and has a lot to offer. But what I see is that we should just extend things. So imagine keeping all that stuff and just adding this, maybe, this tough guy who's also kind of really concerned with what he looks like and stuff. And then these guys. So this is a photo from a workshop that I taught last summer also. So I think you get a sense here of just this, how different this stuff looks, yeah? But that's all computer science. Computer science and engineering, it can look like this. These kinds of people can do it. So I think we as disciplines need to embrace these people and kind of open things up to do things that look like this, that feel like this, that embrace these types of people. So these are people that could be doing this stuff, but they're not just because they think that they know what CS and EE are, and they think that they're not interested in, but it can look different ways, and people can do different things, and we should think about that.